Professor Scalia went over this type of problem in lecture, but I wanted to kind of give you guys a chance to try it yourself or just really emphasize it here. So this W value, we've been taking a general constant for simple harmonic motion. We want to know a couple of things though. Where does it come from? Because it's not necessarily the same for every type of harmonic motion problem. This W is something that you find. We know it to be true for a lot of particular problems where if we have, for example, like a vertical mass on a spring or horizontal mass on a spring, if there aren't any kind of strange operating conditions, we can just sort of treat it as a regular problem. In this case, what we're going to do is we're going to go through and just kind of look at the free body diagram and try to understand why we end up with this expression and what this is. Okay, so let's look at this. So we have this little 2 up here and this little 2 down here. So what does that mean? So when we have these little superscripts, that means that it's the second derivative, okay? So what that really means is that when I have the second derivative of position with respect to time, that's really just like acceleration, right? Y. So if I take the derivative of x with respect to time, right, that's going to be velocity, right? And then if I take the derivative of velocity with respect to time, that's acceleration, right? So acceleration would be like dx over dt. And then I would take like, right, d over dt of dx over dt. And that's what gives me that like, so that's what it means, but it's the same as acceleration, right? Okay. So what we're going to do is we're going to set up our free body diagram and we're just going to label acceleration as this, right? And then hopefully kind of make things a little friendlier and try to understand where these things are coming from and how to find our W. So it's a little bit of calculus here. So bear with me. Okay. So we're going to start with our spring. Okay. So this is my equilibrium point. Okay. So this is just what I'm going to model as my 0 basically for x. And then I have a spring, some spring here. And then my mass is going to start, I have it over here. Okay. Maybe I'll move it down so it actually looks like it's on the surface here. Okay. And it is oscillating. So I'm going to do a free body diagram for my mass. So I have a couple of things happening. So if I'm going to model it as a point mass, okay, I have the weight, okay, I have the force of the spring that's pulling back, right, because it's past the equilibrium point, and so that spring force is going to be trying to pull it back towards the equilibrium point, no matter where the mass is. If the spring is not at the equilibrium point, the force will always try to pull it back towards the equilibrium point. Okay, cool. So then we also have our normal force. So, okay, so for our sum of forces in the x, right, we have this negative Fs for the spring. And then for our sum of forces in the y, we have this n minus mg, right? That's all that's really going on here. So let's look at what's going on with our acceleration. So for a y, okay, we have a 0. What about AX? AX, we do have an acceleration in the X direction, right? We're oscillating back and forth. And unlike previous problems where we've really only dealt with like constant acceleration, for these simple harmonic motion problems, the acceleration is not constant, right? This is like moving the entire time. So our acceleration is as a function of time, which is why we model it this way, okay? So we're going to say our acceleration in the X direction, we are going to label it as the second derivative, right, with respect to time. Sorry, these look like partials. I think that's just my handwriting. They shouldn't, so if you don't know what I'm saying, so this is a normal derivative d. This usually means like partial. So not the most important thing ever because we are treating everything else like a constant, but it's fine. Okay, so we're just labeling our acceleration as the second derivative of the position with respect to time, right? And that helps us, right? Because when we know that if we model x of t as this general solution, this is something we can take multiple derivatives of, right? This helps us solve our problem. So this is something very useful to know because we're relating our acceleration to what we start with for x. Okay, so basic free body diagram, basic forces. Now let's look at what's going on here. Okay, so let's set our, so some forces in the y, so we have 0 is equal to n minus mg, nothing crazy there. And then for f of x, so sum of f of x is going to be equal to m times ax, right? Which is, so this is sum of f of y, and this is sum of f of x, just transferred down, right? Okay, max, and then we have minus fs, which is going to be equal to this kx. So we have minus kx. Just want to make sure that the negative is correct here. I believe it is. Hopefully nothing's strange. Yep, minus kx here. Okay. We don't want to take our negative twice, so just kind of be careful with that one. Okay, so now for our ax, let's plug that in. So we have d squared over t squared. So the second derivative with respect to x times m is equal to negative kx. So this is actually a second order differential equation. When we say second order, what that means is just like, you see this 2 here? It's a second derivative, so second order. Okay. So k over m x. So I just moved stuff over. Okay, so now, wow, look, we have that equation that we started with at the beginning of our problem. So that's where that came from, really. This is really just saying like acceleration is equal to negative k over m times x, right? So we have, so this acceleration is a function of position. So what that means is we need to kind of like, so this x is like an x of t, right? This isn't a constant x, this is an x of t. So we want to try to figure out what acceleration is in terms of this, this x of t value. So we're trying to solve for it. Okay, so we're going to do some interesting gymnastics here. Okay, so, okay, let's figure out what this means. Okay, so we're gonna kind of come full circle here. All right, so we are going to take our expression using this general solution, and we want to try to figure out this W value. So we want to figure out our frequency, right? This oscillation frequency as it's going back and forth, right? As this block is shifting and oscillating back and forth. Okay, so we'll say that this is like some A, this is to some negative A. Okay, so let's use our expression for X. So what we're gonna do is we're actually just gonna plug it in, right, to our expression for the, we're gonna take 2 derivatives of the actual X expression, and then we're gonna set it equal to, or we're gonna try to like see what it is. So we're basically guessing the solution to this problem, and trying to answer some questions for ourselves here. Okay, so we're gonna take this as our solution, and we're gonna say like, okay, we're gonna guess that this is the solution. X of t is equal to a cosine of wt plus b sine of wt. So we're gonna say like, okay, I think that this is my solution to this. And what I'm gonna do is I'm gonna take 2 derivatives of it, okay? And like just check and see if it'll work, okay? So let's see. So let's do dx of t with respect to time. Okay, so my first derivative of this is going to turn into negative a w sine of wt, right? Plus, oh, sorry, minus. Nope, sorry, plus b cosine of wt. Okay, so far so good. All right, now I want a second derivative. So let's do this again. Negative a w squared cosine of wt minus, oh, sorry, I forgot that w up here. We're doing chain rule, right? So we have to take the derivative of the inside part as well. So minus bw squared sine of wt. And notice the cosines and sines are just going to kind of keep switching this whole time. Okay, so, and that's equal to the second derivative, right, of x of t with respect to tm, with respect to time, sorry. Okay, so now here's where things get kind of interesting. So I can pull out This is how we're solving for W, right? This is how it happens. This is the magic. Negative W squared, and then we have A cosine of WT plus sine of, oops, sorry, plus B sine of WT. So what happened here? Well, we got x of t back, right? This is still x of t, right? So if we say that our second derivative of this, right, is equal to some W squared, right, times x of t, well, let's look what we found up here. So this x here is some x of t value, right? X of t. And we solved for our x of t, right? It was hard because we have it on both sides, right? This is the derivative of x of t, second derivative with respect to time, and we have it on both sides of the equation. So when we solve for this differential equation, sometimes we have to make this guess and then just kind of see if it matches our solution. And this is just sort of the common guess for when we have a simple harmonic motion system. Okay, so yeah, so this works. So what's happening here is now we're basically saying that this W squared is equal to K over M. So we find our frequency for this system to be equal to the square root of K over M. Okay, so we couldn't just separate it and do like what we might consider math that we're more comfortable with, because these are both functions of time. So we have x of t on one side and x of t on the other side, and we don't know anything about it, okay? And we really need to find that before we find anything else. And so the way that we were able to solve it was just by guess and check, okay? So once we have x of t, we can basically solve both sides of the equation at the same time. So I know that that's like a little counterintuitive, but I guess as a general rule, what I would leave you with here is, so if I set up my free body diagram, and I look at where things are oscillating, right? I look at where things are oscillating, and I can set that acceleration equal to the second derivative of position with respect to time, right? And then I have a differential equation here, right? And then I just choose my x of t value, okay? And I take that derivative. I can solve for, or take my second derivative, I can solve for this w. There are some special cases where we kind of have to do some tricky math, where we do a small angle approximation, and we'll look at that a little bit more on Wednesday. But today we're going to try to just stick to the spring problems, but just know that there are a few other edge cases. But hopefully that makes a little bit of sense as to why we solve for that W in this way. And so if you have a problem where like the configuration is a little bit different, or there's like some kind of an edge case, this is sort of the approach to actually solving for your W. Okay, but we'll go over more of them so you can understand when and when it's just standard and when you would actually try to solve for it. Because most of the time for a lot of these systems, it's just sort of the standard value for simple harmonic motion. This will get you really far. Okay. All right, let's move on to the next problem.